I have one take-home message for you about climate change and water, and it's this. Climate change is really about the water cycle stupid. Climate change and the water cycle, they're joined at the hip. And when people talk about global warming, they really miss the point of the connection in the Earth's system between how water moves around and temperatures. And that's really the basis of this talk. This is Lake Powell in 2004. After an extended drought, we may be out of it, we're not sure. The reservoirs don't know yet that they're out of a drought. But 2/3 of Lake Powell is missing there in 2004 with potentially enormous implications for this state. So I've got 7 quick parts to this talk. And the first are a whole bunch of slides on how the water cycle itself changes under global warming, under climate change. And these slides all come from a document released in 2009 by the White House that I had the privilege, along with about 30 other scientists, to author. And we had, I think, 7 different sectors. And because water was so important, it came first in this document. So that gets to my key point again. It's about the water cycle stupid. And here's where you can get the document. It's designed to be read by the public. It's not a dense climate change document. It's really quite easily readable. So there's a whole series of key points, one of which is that climate change is going to stress water resources. And here's the area where we think it will dry in the US. Here's where it gets wetter. And here's where people have moved in the last 30 years. You can see an interesting correlation there, which has all kinds of implications for those of us in the American Southwest. Water cycle changes in fundamental ways. It's the primary mechanism by which the Earth moves heat from areas where it's got too much heat to areas where it's too little. It's the water cycle that does that. And it does it in the form of big ocean currents like the Gulf Stream. And it actually does it in the form of water vapor, which when it evaporates actually absorbs energy, and when that water vapor condenses somewhere else, it releases that energy. That energy in the water vapor, it's what drives hurricanes and thunderstorms and tornadoes. It's quite pronounced, and because the Earth will differentially heat, the poles are heating twice as fast as the equator right now, we think all kinds of weather patterns change and the water cycle as well. But there's another thing that goes on with the water cycle as the Earth heats up that makes things different. And that is that the Earth's atmosphere holds a lot more moisture with just a little bit of warming. In fact, for every 1 Fahrenheit increase, there's a potential to hold 5% or 4% more moisture. So if you have 5 Fahrenheit warming, you now have 20% more moisture capability in the atmosphere. Atmosphere is this big sponge above our heads, and it will absorb more. And guess what? When you wring it out, it actually comes out in bigger downpours under a warmer climate. And one of the basic rules is wet areas in the climate get wetter and dry areas get drier, and the climate models are very good at showing this to us. It's changing already. You can see it around the planet. Snow cover, mountain snow water equivalent, annual precip is changing in different areas. Runoff and stream flow. Amount of ice throughout the planet is changing in different areas, mostly going down. Ice cover on lakes and rivers, we're seeing these things right now. Floods and droughts, more common. These are increase in very heavy precipitation days over the last 50 years, more in the wet part of the US, but also quite a bit elsewhere. And precipitation intensity, we'll see more of these extreme events going forward. Floods and droughts, again, on the drought side, these are projections for the American Southwest at 2100. And an important note is that we expect the storm track to actually shift northward, to shift poleward. And I'll explain a little bit later about why we think that's going to happen, why we think we're already seeing it happen, and the implications for us. We're going to see, on a global scale, more evaporation, more precipitation, but regional winners and losers. And again, you've seen this image already, drying in the west, more in the wetter portions of the US. You can see it here with the poles, with Alaska getting wetter generally, and the southern portion getting drier. Snow-dominated areas are going to experience particular changes. This is a look at observed trends in runoff timing 20 days earlier in large parts of the West over the last 50 years. This is a projection out to the end of century. In some places, almost 35 days later. And there's a new study in Colorado by Dave Clow at the USGS, which talks about we're actually seeing that now here in Colorado. For a while, we weren't. And there's some good evidence here that our elevation actually provides us with a bit of a buffer on some of these changes that we expect to see in snow-dominated areas. But we're not immune from them. In fact, there are all these differential things that go on under climate change. And one thing that may very well go on is that our ski industry stays healthy while other areas do not if they're at lower elevations. Sort of an interesting thing to think about, potentially, at least for a while. A common thing we see in snow-dominated areas is a shift in the annual pattern of runoff. So here's January through December, here's the amount of flow. Here's what it looks like presently at the Green River. You expect to see these hydrographs shift earlier in the year. You expect this descending limb to stay lower longer with warmer temperatures out here in the stream flow in the latter portion of the year. Changes to water quality and groundwater. In the case of water quality, a lot is not known here, but one thing you can say for certain is that river temperatures, stream temperatures will go up because they're strongly correlated with air temperatures. Warming air temperatures means only one thing. And in a lot of places, warmer water temperature actually means less dissolved oxygen, less oxygen for animals and fish and the like in rivers, and yet they actually will have a higher metabolism because of the increase in temperatures. I find it interesting that people love to talk about climate change, but a lot of times it isn't put in the context of everything else that's going on the planet right now. 6.5 billion people going to 9 billion. This is a very different time of humanity, for humanity. And this applies to the water cycle and water systems as well. Everywhere you look, we're already having water conflicts. And we have water systems that are stressed by aging infrastructure in particular. And so we're adding yet another stressor onto existing already problems. And that's frequently what happens in climate change. If you just had to deal with the climate change impacts alone, we could handle it, but it's the combination of these other factors that makes life very challenging. And it's very true in the case of the water sector. All water management in the 20th century was predicated on this great historical, in many cases, 100-year gauge record we had. And if you could manage to that gauge record, those droughts and those floods, you could do just fine. But because of the change in the water cycle, we now know that those past records are going to be less and less valuable going forward in the 21st century. And it's a huge conundrum to people who operate our water systems. What kind of planning horizon, what kind of planning features do you now utilize? And the answer is we don't know. And there is a whole lot of work going on right now trying to figure this out. The one point I guess I would make, and it's one of my key points at the end, is we need to design for robustness and resiliency in the 21st century. Those are kind of two of the big buzzwords here. And we can no longer optimize to the conditions of the 20th century, which will mean actually more money in a lot of cases to build systems that are more robust. Water's connected to all kinds of other sectors. I mean, you know this: human health, agriculture, energy supply, ecosystems. And I could give a whole talk on this one, the connection between water and energy. 80% of our thermal power, or 80% of our total power, is thermally generated. That almost inevitably uses water for cooling. So you have no energy without water. Most people at least get an idea of that, but they don't understand the opposite. They don't understand how tied energy is into our water systems right now. In this state, we've actually been able to use gravity to our advantage, but there are enormous projects in the American West, like the Central Arizona Project, which pumps water 300 miles and 3,000 vertical feet into Tucson and Phoenix. That project uses 400 megawatts of power to move water around. Water's heavy, it's 8 pounds a gallon, it also has this what's called a high specific heat capacity, which is why it's so great to take a shower in it. Once you heat it up, it stays warm, right? But there's a lot of energy that you use in heating it up. And those two facts, the fact that it's heavy and it has this high specific heat, means that energy, and it takes a lot of energy when you're dealing with water. When we go forward in the 21st century, everything we do, both with regard to energy and with regard to water, they have to think more about each other right now. And again, I could give a whole talk on this because it's fascinating and a lot of work is going on. All right, what about climate change and studies that have been done in the Colorado River Basin? Arguably, the most heavily studied area in the planet with regard to climate change because of American scientists and because of the dryness and aridity of the basin and the challenges that exist. These studies go back actually to 1980, which is quite early in the scientific realm with regard to climate change, although I will point out that climate change is not new. Fourier in 1812, I want to say, suggested that there was something weird going on in the planet, that it was warmer than it should be, and he didn't know what it was. And in about 1860, we began to figure out exactly what it was, that there were greenhouse gases that caused this. So don't let anybody tell you that climate change, somebody just made this up in the last 30 years. The history on this goes back almost 200 years. But there are a whole bunch of studies here, including a whole bunch since 2004. And most of these point, well, all of them, for the most part, point to reductions in Colorado River flow. Half the water in the Front Range in some years is Colorado River water. So don't think because we live out of the basin here, we're somehow immune to what goes on in the Colorado River Basin. This is a study we did for the state of Colorado. It's called Climate Change in Colorado. It was done for the Colorado Water Conservation Board in 2008. Peer-reviewed, released by my entity, the Western Water Assessment at the University of Colorado, but input from NCAR, input from Colorado State, input from a whole bunch of different people. It's got 5 chapters. It's on the Colorado Water Conservation Board website. I encourage you to read it. There's a nice chapter on climate models, a nice chapter on trends, a nice chapter on projections. But these are the same studies on the Colorado River showing actually 6 to 20% reduction by 2050 on average in that system, with enormous implications for this state. Here's a look at warming and precipitation changes at 2100 under a moderate kind of mid-range emission scenarios. 4 Fahrenheit in the summer warming. That is a lot of warming. Last ice age was about 5. All right, so 4C, the last ice age was about 5C colder than now, to give you an idea how much warming 4C is. And here's winter precip, which is mostly what's important here. And that's Boulder right there. Wet to the north, dry to the south. We think this dryness moves northward. How much it moves is a really big question. And it's a question we don't have the answer for, but it obviously has huge implications for us. You've seen this many times now. This is Chris Milley's work, but it's really important to look at it. This is very good model agreement where you have all these dashed lines, and it really should be here as well. It's about 20% in the Colorado River Basin by this one study, which is admittedly a crude effort. So why are we so worried? Why am I so worried about what goes on in Colorado? Major deserts of the world sit at 30 degrees north and 30 degrees south. You can see them here. And why do they sit there? What goes on with these deserts? Why do they exist 30 degrees north, 30 degrees south? George Hadley in the 1700s figured this out. And it's a really beautiful theory. It still exists to this day. And basically, his theory explains why we have so much evaporation at the equator, why the trade winds blow northeast, north of the equator, southeast, south of it, why these deserts exist at 30 degrees north and 30 degrees south. And effectively what happens here is you get lots of evaporating water from solar energy at the equator. That evaporating water rises, rising air cools, cooling air can't hold as much precipitation, so it precipitates out, you get a lot of rain. Then whatever's left moves poleward, splits and moves poleward. And then it tends to descend at 30 degrees north and 30 degrees south. Descending air does exactly the opposite of rising air. It dries out what sits underneath it. And that's why these deserts sit at 30 degrees north and 30 degrees south. And the trade winds come about as this air completes its circular pattern and returns to the equator. And because of the spinning of the Earth, it takes on this northeast or southeast component. What Hadley did not know about were jet streams that sit right at the edge of these Hadley cells. And jet streams both create weather, and once it's created, they then cause it to track. We think these Hadley cells expand. They actually get bigger in a warmer world. And that has all kinds of implications for us because of the Great American Desert that sits to our south and what exactly happens to that desert. How far north does it move? All right, what about what's gone on recently? This is Colorado River Basin, and this is probably too hard to see in the back, but effectively, not much change in annual precip going back to 1895. Very, very busy signal. But look at the warming here in the American West, and you can look at this run up here, about 1.6 Fahrenheit since over this long-term average. And you can make a very good case that the recent drought in the Colorado River Basin has been exacerbated by this warming, and I'll show you a slide on that in a second. Here's annual flow at Lee's Ferry. And Max, you talked about the Udalls. I actually like to talk a little bit about John D. Lee, who's actually my great-great-grandfather. He had 21 wives. Lee's Ferry is the dividing point on the Colorado River between the upper basin and the lower basin. And 21 wives is kind of exhausting just to think about it, isn't it? A very interesting historical character. So if you go back and take all the records from 1906 on and make 10-year running overlapping series and figure out how much water was in them, you come up with and then you rank them. You come up with this list. And the top four, or actually the bottom four, I should say, in terms of runoff, are in this current drought here. You have to go back to the fifth of these, which started in 1959, went through 68 to get one out of this period. And what's interesting is the difference between this number and this number. It's 5 million acre feet. That's 50 vertical feet in Lake Mead, the single biggest reservoir in the United States, which is 130 feet low right now. If we had, again, to say that again, if we had the second worst drought, not this current one, Lake Mead, instead of being 130 feet low, would be 80 feet low. There'd be 5 million extra feet of water in it. That's the difference between this current drought and the next worst one. The one where we did most of our planning for droughts is on that particular drought right there. This drought is really quite different, and it's because of the temperatures we've seen. That's my operating hypothesis here. I won't bore you with this. This is just flows year by year. We may actually have a good year this year. Reclamation released this slide 1923 up through 2005. Here's demand and here's supply, and look what happened right there. You cannot have demand and supply cross. You cannot have it in a big system. You will run your reservoirs dry. And that's what we've seen the last few years. That's why the two biggest reservoirs in the United States, which started out full in the year 2000, now have only half of what they had in them now. And here's a look at what went on in Lake Mead in red and Lake Powell in blue. Full in 2000 and this precipitous decline. And if this were truly up to date, it would actually be below this point right here, or actually it would have dipped below it and then come back. At one point in November, Lake Mead was lower than it had ever been since its initial filling in May of 1937. And I'll tell you why that is. If Lake Mead continues to drop, all kinds of bad stuff happens, including losing power production and a whole series of declared shortages in the lower basin, with Arizona and Nevada online for most of these shortages. Upper basin states of Colorado, Wyoming, Utah, and New Mexico are protected from these shortages, but not from another kind of problem. And that's what I'm going to talk about here. So here's the problem in the lower basin, those three states, Arizona, Colorado, and Nevada. Legally, they're entitled to 9 million acre feet of inflow every year, and they've been letting out 10.4, like clockwork. It doesn't take a scientist to figure out you can't do that forever, because you got a 1.4 million acre-foot hole you're digging in your reservoir. This is all they're legally entitled to get. And yet they've built a system around this. Why have they done that? Because the upper basin has not used its entire amount of allocation, and because we've had plenty of water in the system. So the Colorado River Compact allows them to borrow, if you will, without having to repay on this extra water. At some point in time, they're going to have to solve this problem. And no one knows exactly when that is. Upper basin growth or climate change reduction in supplies, either one of those will force this issue. And I'll note that that whole amount, almost that whole amount, falls on the state of Arizona based on the 1968 Act, which created the Central Arizona Project. And it's really untenable in a lot of ways. Arizona can deal with about half that loss, but they can't deal with all of it. And in many ways, this is the classic collision between 19th century water law, 20th century infrastructure, which we can't very much change right now. You're not going to build your way out of this. And 21st century population growth and climate change. It's the classic conundrum in the water world. But what about the upper basin? What about Colorado? Well, because of a very weird added, I almost call it an artifact of the Colorado River Compact, an added on item at the very end of the negotiations, we have what some people call a delivery obligation, although the lawyers hate that term. There's a clause in there that says every 10 running years, the upper basin shall not cause the flow at Lee's Ferry to fall below 75 million acre feet every year. The upper basin gets whatever is left over. And the problem is we don't know what that number is. Growth and climate change makes that number clearly smaller. And there's been an effort underway in this state to put a number on that. But really, in large part, that effort, I think, is misguided, and people through the Interbasin Compact Committee have figured out it's misguided. It's the wrong question, how much water is left to develop. The right question is, how do you build robustness and resiliency in our water system so you don't ever have to deal with what people call a compact call, where we would potentially have to curtail uses so that we could send water to the lower basin. This is that study I talked about. It's called CARWASH, humorously, Colorado River Water Availability Study. And these are a whole series of graphs that show how much water is in the river to develop going back many years. And a lot of them are between 500,000 acre feet, 500,000, and 1 million acre feet. This is the new one. We actually think that number's less than 0 if you did the study correctly. It's a huge range. And it's one of the reasons why under climate change, we cannot go back to the 20th century idea of taking these records and saying, okay, what is it that's there? We'll plan for that. We have to be smarter in the future. All right, what about some of the fun science issues? One, our models right now are not at the right scale to help us figure some of these questions out. Many of the images I've been showing you are from the very big global climate models, which are terrific on a global scale, but not so good on a regional scale. And this probably doesn't show up too well, but in the Colorado River case, almost all of the runoff comes from a greater than 9,000 feet. It comes from this area. This is percentage and this is elevation. And here's basin area. You've got to model these higher elevation areas correctly. And right now we're limited by computer power and by some degree brain power to get this done. But there's a scientist who's worked on dust on snow. And this has been a very interesting phenomenon. Here's clean snow, here's dusty snow. Basically, dusty snow absorbs a lot more solar energy in the springtime. It melts faster, we know that. Here's some modeling results. Clean snow on the right, so day of year, and this is amount of snow water equivalent here. So if you had clean snow, you go out to day 190 in the year until your snow's all gone. A little bit of climate change are these two lines right here. Here's what happens if you put dust on it. In this case, almost 50 days advance in runoff timing. And one of the things that a recently released paper that I was one of the co-authors on, along with Tom Painter, 3 weeks earlier peak in the runoff, and we think 5% less runoff is occurring in the Colorado River Basin since 1850, since humans, European settlement of the American West. Grazing, ORVs now, construction, a variety of activities that disturb soil in the American Southwest that then gets blown in the springtime and ends up on top of our snowpack. Here's the snowpack in 2008, relatively clean year. Here's 2009, a relatively dirty year. 51-day earlier runoff, we think, in 2009. These other years, we think it happened about 28 days earlier. Again, on average, we think it's about 21-day runoff timing, but more importantly, a 5% loss of flow in the river. The car wash study I mentioned talks about increases in demand. Average increase 20% by mid-century or 2040. 18-day longer growing season at 2070, 30-day longer growing season. And here's, if you go out and look at Delta, here's what the months of the year and the amount of water you need. Here's what we're doing right now, and these are a whole bunch of different models in the future. You can't really see the advance in timing, but what you can see is every month of the year you need more water for the same crop. Pine beetles, everybody knows this story. Again, the classic case of humans doing something, the climate doing something, and combining collectively in a way that gives us a bad outcome. And here's Colorado. If you think we got a bad, look at British Columbia and their mountain pine beetle. No one really knows what this means in the long run. We just don't know. A lot of issues, some speculation that you might get more runoff in the short term. What about reservoirs? In 2008, these two Scripps researchers released a paper that said by 2021, Lake Powell and Lake Mead could be dry 50% of the time by 2021. And it raised a big stink because the water managers did not like this. And we got involved, some other people got involved. And intriguingly, we actually did another study at the University of Colorado. And we more or less decided, well, they had it right, they just had the timing wrong. It's not 2021, it's probably 2035 or 2040 if we continue down the same path. And a lot of it depends on whether or not you have no climate change, a 10% flow reduction, or a 20% flow reduction. This is risk, if you will, of running your reservoirs dry under different kinds of scenarios. 25% at 2057 with a 10%, 50% though at the same time horizon with a 20% flow reduction. We were actually surprised because the original study people really complained about, and there were some errors in it. But nonetheless, there's a problem out here in the not too distant future based on demand and supply in the Colorado River Basin. I mostly talked about this, just we're on a collision course between supply and demand. All right, some closing thoughts. So this is a study out of, it's not even a study, it's a little editorial in Nature that came out earlier in February 2010. And it was really a warning both to climate modelers as well as to people who would use their output. And it effectively says, you know, these models, they're very important. We need to use them for science. But on a regional level, they're not telling us what we need to know, and they probably won't, and we need to be very careful about using them. And so I'm not an anti-modeler, but what I am telling you is that the initial attempts in the early 2000s to try and figure out what to do about the future based on model output is only part of where we need to go to get the answers we want on a regional basis, not on a global basis. The models are really quite good on a global basis, but on a regional basis for water supply planning, there are a whole host of issues here, and we need to be very smart about this. So don't get me wrong, I love the models. Lawrence Buja from NCAR is right back here. He's a climate model extraordinaire. Raise your hand, Lawrence, because we have all this great talent in this state. Don't get me wrong, they're really important, and Lawrence is working with a variety of water providers in the West. But we're going to have to expand our horizon because this is a very difficult problem on how to build robust and resilient systems. And the models are only part of the solution here. So 5 take-home points. Climate change and the water cycle, they're joined at the hip. I sometimes say most of the really important impacts of climate change will be delivered through changes in the water cycle. And that's the only lie to that is sea level rise. But here in Colorado, we don't have to live with that. And I think you can also make a case that sea level rise really is a change in the water cycle. It's not a change in the water cycle as many people normally think about the water cycle, but effectively we're raising glaciers, we're melting glaciers, and raising sea level, and water stored in those glaciers really is part of the water cycle, albeit a very long circulating water cycle. Big fundamental changes in the water cycle are coming at us. Declines in the Colorado River are likely in the 21st century. The Colorado River climate risk, it's borne by the upper basin states because of this weird added on Part 3D, that's the so-called delivery requirement, where we don't know how much water we're entitled to. And we need to integrate robustness and resiliency, which I've made multiple times. Then let me mention finally one thing. We're going to release this report today. It was commissioned by Governor Ritter. It's called the Colorado Climate Preparedness Project. This state has done a study of the science with regard to climate change, and I showed you that. That was that Colorado Water Conservation Board report. The state has not done what many people call an impact study. That is to say, not what kind of impacts is the climate going to cause physically, how much warmer, how less water, but impacts in terms of what does this mean for skiing, what does it mean for agriculture, what does it mean for human health. The state has not done that. And in lieu of doing that, Governor Ritter, because he was departing, wanted to take a look at what was going on in the state with respect to climate change adaptation. And so we put together this effort at the University of Colorado that we're going to release that looks at 5 different sectors in the state. Let's see. Water, outdoor recreation, electricity, agriculture, and forests and ecosystems. And it's an attempt to look at the different people that are working on climate-related issues, the different projects that are underway, and any actual products that are out there. And we did this with the idea we would hand it over to Governor Hickenlooper and say, climate adaptation is a big deal. We understand that everybody wants to cut carbon, and that we need to do as well. But we also have to prepare for lots of changes that are coming forward, and that requires a fundamentally different mindset. Hence this project and the document, the 100-page document that we're going to release today, along with a website that details the people and products and projects that are underway. So I think that's it. Yeah. So the first point I'll make is that the demand side of climate change really has been much less studied than the supply side. And that goes for big entities like Denver Water and the Water Research Foundation, which are here, and even in the scientific literature. You were asking specifically, and in the case of the Colorado River Water Availability Study, they had even population, let me think about that. I think they had even population for the first part of this study. There's a phase 2, which is going to increase these demands, but they wanted to do it right now with a constant look to see how that would change. They know that's not right, but in the future, you're going to see increased evapotranspiration out of plants, longer growing season, the like. And the research on that's actually pretty thin, believe it or not.
So it could be much worse.
It could be worse. It could be worse. I am not, one of the things you'll find in this world, in the climate world, is there are meteorologists who really work on the weather side, and there are people, climatologists, although the climate scientists I know don't really like the term climatologist because it refers to these old people who used to keep records. That's sort of what they did, was kept degrees every day and the like. But there's a difference between people who study meteorology and people who study climatology. I'm far more on the climatology than the meteorology side. I don't work on the tornado side, and I can't help you. There have been tornadoes at this time of year before, but not all that often. And you get at one thing that's really interesting. Everybody wants to attribute events to climate change, right? I mean, it's kind of on the tip of our tongue always. Was this climate change? And the thing I will tell you is that the statistical hurdles frequently to say that without a doubt from the scientific side are very, very high. So frequently we can't say that. What we can say is it's consistent with what we think should go on, but I can't give you a statistical number that says, okay, 1 in 20 chance that this happened by chance, and 19 out of 20 times it was caused by climate change. And you're not going to see that because of the statistical hurdles that are involved. And it's something we're just going to have to get used to and live with. And also realize that there are all these other things going on. You know, for example, when you look at the disaster literature right now, losses keep going up and up and up. Well, it's easy to think that's climate change, but in point of fact, in the case of coastal zones, there's far more property at risk right now than there ever has been. And it's the combination of the two. It's not just climate change, it's climate change and everything else going on that's causing problems. So, long-winded answer, yes, sir. You know, population is a huge problem. And it's a problem that has almost been excised from our vocabulary. Some people like to say if you don't solve the population problem, no other problems matter. At some point, we're going to have to deal with this. And again, it's the combination of these that will make this century so interesting in some ways, terrifying, I think, in other ways. And you know, when you deal with the skeptics, they really dislike the fact that everything is climate change, climate change, climate change. And that's partly why I try and talk about these other issues that are going on out there that are really serious. I mean, I have a whole talk I can give you on how we've perturbed the nitrogen cycle, which would probably bore you all to death and to tears. But basically, we are indiscriminately fertilizing the entire world right now with nitrogen. And it is not a good thing. There are 400 dead zones around the planet right now in estuaries, the Gulf of Mexico being one of the largest, but 399 ones elsewhere from agricultural fertilizer, from burning fossil fuels that contain nitrogen, from planting actually more nitrogen-fixing plants that have ever been there before. 40% of the people are alive today on this planet because we can artificially pull nitrogen out of the air and make fertilizer and feed them with it. Huge implications with our perturbation of the nitrogen cycle. Yeah, no, I think there are a whole variety of things you can do. So the last year I've spent two-week trips in Australia. So I spent a month there. And I'm going to go spend 3 months at the invitation of the government of the state of South Australia to study what they're doing with regard to their water business down there. They are totally revamping how they think about water in that country. They use a term that you barely hear, water security in Australia. And when they use security, they mean it. They mean it like we mean national security. They're doing everything down there, from trying to establish really robust water markets, which I think ultimately will come here at some point in time. We have this tremendous tool to wring efficiency out of our social systems, and they're called markets. And to date, our water systems, for a variety of reasons, have more or less been excluded from those. The Australians are teaching us how to do it right, how to protect environmental values, how to protect social values while still having these markets. That's one case. I think you're going to see a lot more interest in conservation. It's not the only solution, but the Australians use a quarter of what we use in some cases, a quarter of the water we use in some cases. It is a zero-sum game, though, in water, and the IBCC, the Interbasin Compact Committee, really understands this right now. Here's our solutions. You can take water out of the Colorado River and develop it. Well, that means less water for fly fishing and for rafting and skiing and snowmaking, all those things. I mean, that's one solution. You can dry up farms, which on the one hand seems like no big deal, but really is an important part of our heritage, an important part of open space values, important part of our history. You can conserve water. Those are sort of the three options we have. There are some recycling options you can do, I suppose, as well. But all of them have downsides. That's the deal with the 21st century. There are no easy solutions.